All right, welcome to another live episode of the Engineers HVAC Podcast. I'm Tony Mormino. I'll be your host today. And a quick shout out to Kevin Quillinen and your family. Kevin was supposed to join us today, but had an emergency in his family. So we hope you're okay, Kevin, and prayers for you and the rest of your crew over there. So thank you so much for joining us. We're going to start part 2 of our Psychrometrics series. So we're doing a 3, maybe 4-part Psychrometrics series if we get enough time to do part 4. And the first one we did a few weeks ago, we talked about the psychrometric chart and building the chart. And today we're gonna talk about, let's see here. We're talking about SHR, sensible heat ratio. We're gonna talk about calculating the CFM and then tons of refrigeration. So we're just basically expanding on the first show and yeah. So we're glad if you're joining us. We hope to see you here. Please ask any questions in the comments. We'll be monitoring them. We're glad to answer them. This particular live PDH does qualify for credits in New York and New Jersey, which is a little bit unique. Hey, Stacy, how you doing today? Stacy's from Arkansas. Thank you, Heather, for the comment there. So, Stacy, we're glad you're here, and we'd love to hear where everyone else is from. Please throw your name and location in the comment, and we'll get started here in just a second. And I hope that you can hearing us okay. Good morning from Virginia, Emmanuel. Good morning. Thank you so much for joining us. We appreciate it. I am located in Asheville, North Carolina. I see Courtney from Nashville. Courtney is on the marketing team and is handling all the background information there. So hi from Jersey. We have a LinkedIn user. Looks great on LinkedIn. Thank you, Heather. Rahman, I'm sorry if I'm not pronouncing that right, but hello. And Steve from Philly, welcome for joining us. Steve Clark, I see. Paul Camiglia, Richmond, Virginia, PE, thank you so much for joining us. Hello from Rockville. Tom Schultz, how are you from Houston? Good to see you. Good evening from Malaysia. Wow, worldwide today. This is great. Let's see here. We have Melvin in Atlanta. Look at all these comments. This is great. Thank you so much for commenting, by the way. It makes this a lot more fun than just sitting here on my own. I see Paul Leonardi. Paul, how are you? From South New Jersey. Andy from Michigan. Rami from Albany, New York. Welcome. Thomas, good to see you. Washington, D.C. Oh, we got hi from San Diego. Brian, Todd, morning from Rochester, New York. Ted Sherwood, Lucian from New Jersey. Praveen from India, welcome. Steve, good morning from Mexico. South Carolina, Jeff, good morning. Right down the street from us. So I'm in North. Comments, you can post those too, but if you got any questions, please feel free to throw them in the comments. So good morning. All right. Well, we're going to get started here in 3, 2, 1, boom. That was pretty good time in there, Heather. I think I got that one down. Okay. Good morning, everybody. Thank you so much for joining us. This starts the official PDH presentation. This is part 2 of our 3-part, maybe 4-part psychrometric series. If we get time to do a part 4, we're going to do one. I think we're gonna. These have been tons of fun. We had probably record attendance for a live event at our last show. I don't remember exactly how many people seen it, but over 800 and many hours a few times. So we say that to say thank you so much for watching and supporting what we do. It's a great chance for us to give back. The Engineers HVAC Podcast is available on all major platforms, and our mission is to empower and educate the commercial HVAC community. So we hope that we are doing that. We hope that we are able to do that, and we appreciate the opportunity to do that. So this particular episode is what we call the Northeast version of the Engineers HVAC Podcast, which is supported by Klima, New York, Klima, New Jersey, ETS, Energy Transfer Solutions, and EBS in New York. And the reason we call it that is because this particular presentation, or this whole series on psychrometrics, is approved for PDH credits in New York and New Jersey, which, if you're familiar with PDH credits, it does take a little bit of extra work to make that happen. So we thank you for New York and New Jersey allowing us to provide these PDH classes. So, and you could email me after the show. Heather will put my email address up in the captions there, and you can email me after the show, and I'll send you the PDH credit. And if you're listening to this in the future, or watching on our YouTube channel, just email me and I'll get you the information here. So, all right, let's go ahead and get started. So, again, this is part 2. We're going to be talking about SHR, sensible heat ratio. Excuse me a second here. We're going to talk about calculating CFM and then tons of refrigeration. So a lot of times, I went through this on the first one. A lot of people are like, oh my gosh, psychrometrics is so boring. It is kind of boring, but it's so super important to understand how to design HVAC systems. And a lot of what we talk about in psychrometrics here in this series and the next one is understanding part load and what happens at part load. One of the biggest mistakes we see is people don't understand what happens at part load. They don't design for it. And then you get some major issues. This is the fundamental foundation of how to understand what happens at part load. So it has to do with the sensible heat ratio, which we're going to dive into a lot today. So why do I need to know this? Because I just said it. It's important to know as a backbone of your HVAC career. So, okay, so here's kind of a recap of what we talked about in part 1. We talked about the properties of air, dry bulb, wet bulb, relative humidity, etc. You can go back and watch that part 1 anytime on our YouTube channel. We talked about building the chart, taking those properties of air and putting all the lines together on the chart. We talked about moving around the chart in terms of psychrometric processes such as cooling, heating, humidification, dehumidification, and combinations thereof. And then we talked about using the chart to determine the air properties given, the dry bulb and wet bulb. You could look it up and get all the other points off the chart. So basic psychrometrics 101. Here's today's agenda. We're going to talk about mixing 2 air streams. What is the resulting conditions you get out of mixing 2 air streams? We're going to do that through an equation. We're going to look at it on the chart. If you have a chart, by the way, you might want to pull it out. You can use that to play along here. So sensible heat ratio, we're going to talk about that and how extremely important it is to understand sensible heat, latent heat, total heat, and then the ratio and why that's important, particularly at part load. We're going to go through calculating air quantities with the sensible heat equation, which is extremely important. Then we'll look at calculating tons of refrigeration. And we're going to finish with just a little bit on full load and part load, which really is a teaser for part 3. Okay, air mixing. Let's get started with that. So the first part, air mixing, we're going to calculate the properties of 2 mixed air streams. And what we're going to do throughout this presentation is refer to this very basic drawing. So what you have here is inside this box represents a chill water air handling unit. You got your cooling coil. For sakes of this discussion, a constant volume supply fan, supply air. You got your return air. And the return air conditions we're going to be dealing with are basically 72 degrees dry bulb, 50% relative humidity, 25% outdoor air for this example, and 95 degree dry, 78 wet bulb. So pretty common design day system, 25% OA, etc. Okay. So what is the condition of this air right here? When you mix the return air and the outside air, how do we calculate the mixed air condition? And if you're new and you're taking notes and you got a sheet where you like to put equations that you use a lot, this is probably one of them you want to put on there. There's going to be a couple I'll point out in this presentation. So this is an important one. Your mixed air temperature is basically your OA temp times the percent of OA plus the return air temp times the percent of return air. Okay. So pretty basic math equation here. Looks something like this. So your mixed air temperature in this case is 95 degrees of outside air times 0.25 plus 72 degrees of return and times 0.75, which equals approximately 77.8. We're going to round up here. So 77.8. So pretty simple, pretty easy. Mixed air temperature. Okay, so what does that look like on the psych chart? Well, let's have a look. Let me pull up my chat here too in case we get any questions. Okay. By the way, again, new format in the studio. I hope this is coming through okay. Heather says it looks good, so I hope you can see it all right. So, okay, let's go ahead and plot the OA and return air on the psychrometric chart for kicks. because we're all about having some fun here. Let's see here. Boom. Okay, 9578. Now, how do we plot this on the chart? So if you remember from the first episode, dry bulb temperatures down here. This is pretty neat. I don't think I've ever used this magnifier tool. So what we do is we find 95 degrees, which is right there. Okay. All right, it's working. My pointer's working. That's good. So we draw a line, 95 degrees, and then we find 78-degree wet bulb. And I'm not going to do this exercise for each point, but just to give you kind of an idea. So 78 is probably 5, 6, 7, 8, right about there. Okay, so 78 wet bulb, 95 dry bulb, and we're going to make a point right there, and that plots our outside air. So won't spend a lot of time doing that again. We know how to do that because we've all watched the first episode, I'm sure, many, many times, right? So let's plot the return air, which is 72 degrees, dry bulb, and 50%. So again, dry bulb's down here. 72 degrees is about right there. And then we're going to draw a line up to the 50% relative humidity, which is right there. And that'll look like that. Okay, so that's your outside air and return air. So how do we show the mixed air temperature? How do we represent that on the psychrometric chart? We just calculated it so we know what it is. Okay. So what we do is we draw a line between the outside air and the return air. And the good news is the mixed air is always going to lie on the straight line between these 2 points. So it's going to be somewhere over here. And you know, since we have way more return air, that is probably going to be somewhere in this region, right? Because you only have 25% outdoor air. Okay, so the mixed air temperature is 77.8, which is right here, 77.8-ish. You draw a line up, draw a circle there, and there's your mixed air temperature. Now, with this mixed air temperature on the psych chart, you can get all the other properties of that air. So we calculated previously the dry bulb mixed air. You plot it here, put this point here. Now you know where the wet bulb is, okay? So the purpose of this is to show that if you plot it out on the psych chart, you can just calculate the dry bulb and they get all the other positions of conditions of that point off of the chart. I actually just did this for somebody. They reached out to me on Facebook and said, hey, can you help me with this? And I did this exact same exercise. So if we were to go over here, you'd see the dew point of that air is, I don't know, 58 degrees, 60 or something like that. The wet bulb is 65, etc. About the same RH, a little bit higher. So, okay, makes sense? All right, I see some thumbs up in there, so that's good. Okay, so if we go back to our diagram here, our basic system, which we're going to be dealing with the whole show, now we have our mixed air temperature. Okay, what we're working towards in the end is the supply air conditions and the CFM. I didn't mention that in the beginning, but that's kind of the point of all this. We're going to get to the supply air and the CFM and the conditions thereof. So, okay, so 77.8, 65 wet bulb. You know, common return air conditions are 80, 67. So we're right in there. Now you are all air mixing geniuses. So just to recap, if you got 2 points in the percentage, calculate the dry bulb, plot it on the chart, and then you can get all the other conditions there. You can use an app, which most people do, and we'll get comments all the time. Hey, I just did my app, but that's great. I really do believe, though, it's important to learn the foundations of it using an old-fashioned psych chart. I have ones here that's pretty tattered and beat up, and I have a bunch of these down here. And when I was new, I would carry one of these around, and I would also carry around something like this, and I would just take measurements, return air, supply air, outside air, and I would plot them on the chart. And it really helped me to see psychrometric processes and understand what's going on. For me, that helps a lot over an app just because I'm a visual person. I use apps too all the time. So, okay, moving on to the next section. Now we're going to talk about sensible heat ratio. In my opinion, this is one of the most important things you're going to learn in these 3 series, because if you don't understand this, it's really hard to understand what happens at part load. And over my career, I've seen so many problems with folks not understanding part load and not designing for the proper equipment and controls to handle part load conditions. So it could be a major, major issue. Okay, so sensible heat ratio. So it describes the ratio of sensible heat load to the total heat load of the space. So what is sensible heat? What is the other part of the total heat, which is latent heat? So there's latent heat versus sensible heat. So for the next couple of slides here, we're going to talk about the difference between sensible and latent heat. And we'll start with the easiest one, which is sensible heat. I actually have some videos here with my new infrared camera, which maybe will help illustrate this point. So sensible heat, there's basically three types. There's conduction, convection, and radiation. So we'll start with conduction. I think this makes sense, right? It's heat transferring through a solid. It works through a point of contact. So this heat is, the heat from the fire is heating up this metal rod. It's conducting through the rod and it comes up to your hand, burns you, yada, yada, yada. So that's conduction. Convection is just another form of conduction, except it's through a gas or a liquid. So in this case, the fire, get my magic wand here. The fire is heating up the air is getting hot, coming up and heating up your hand. So that's convection. Same principle as a heater, electric heater, gas heater, etc. Then you have radiation or radiant heat, which is the electromagnetic light waves, similar to what happens when the sun hits a surface. Okay, so it can be 40 degrees outside, but the sunlight could be hitting you and you could feel warm. That's because of the radiant energy. How that actually works, I have no idea, but I know that's what it does, right? All right, so sensible heat, easiest way to understand that is to understand dry bulb temperature. So it's measured with just a standard thermometer. Okay, there's a picture of me one there. I don't know why I had to grab this, but I like using the props. But the temperature you see on a standard thermometer, if it's a summer day and you walk out to your porch and you have an old thermometer on the wall, that's reading the sensible heat. The important thing to note is it's independent of moisture in there. It does not care how wet it is out. It just is measuring sensible heat. It just is measuring, I want to say dry heat. I'm not sure if that's actually true, but anyway, it doesn't matter how much moisture is in there. That's the point. So in your buildings, in your typical buildings, you have many devices that generate sensible heat. And we'll talk about a few of those here. So anything that's plugged in, I believe generates sensible heat. I don't know of anything that doesn't. Maybe something doesn't. I don't know. Even the refrigerator generates heat out the back of it. You have humans, which put off heat. And if I remember right, 250 BTUs sensible, 250 latent. We'll talk about that in a minute. That's typical human heat generation. Copiers, printers, anything like that. So anything that's plugged in is providing sensible heat to the space, okay? The heat's coming off of it is just sensible. It doesn't have a moisture component to it. So I got this new tool, which is a little infrared camera that I hook up to my iPhone. So I went around and took some videos that maybe will illustrate sensible heat a little better. So this right here is the lounge back here behind our office. If you look at that from a sensible heat standpoint, you'll see that's the refrigerator. That's the lights. There was something plugged in here in the corner, but I can't remember what it was, and it shows you the temperatures. 80-ish degrees is the red stuff there. And there's not much else going on in the space. So what you see in other areas. So all that you're seeing there is sensible heat. These devices are adding sensible heat to the space. So this little video clip illustrates, this is a good illustrates. Heather said it looks like the Predator movie. I know, right? So this video is to illustrate all the different types of heat we talked about, sensible heat, but really a good one for radiant heat. So you see all the sunlight coming in there. So, okay, so if you take, I was wondering where that noise was coming from. It's from that video I was just showing. Okay, so that's the infrared version of it. So you can see there's a lot of radiant heat coming in through the windows. There's conductive heat coming in through the metal frames. And there's some convection coming in as well, I'm sure, if there's some leaks and some infiltration, et cetera. So, okay, here's another video of the roof. And this is, a major heat source for buildings, obviously, is sun. So you can imagine what this is going to look like. So the temperature outside yesterday was about 72-ish degrees, 50% RH. But you can see, because of the radiant heat from the sun, your roof deck's 90 to 100. It kind of jumps around a little bit. And then the deck itself is, I have a better picture. This shows 120 on the deck here. So anyway, more radiant heat examples. And in this office, this is a picture of our office here. You would not believe how much stuff is in front of me if I turn this camera on. Well, you would believe it because you're seeing a video of it right there, but there's tons of heat generation in this office here. And what that looks like infrared wise is this here. So you can see the computer, even the little plug for the computer. Here's my mouse. This is where my hand was. You still see a little red. Screens range from 80 to 90 degrees, something like that. And then I've got this little coffee thing over here, which is this right here. So all sensible heat. And then there's humans. That's me yesterday getting ready for this. So humans put off a lot of sensible heat as well. Okay. And latent heat, which we'll talk about. So it's just a unit heater here. I'm not going to show the video here, but as you can imagine, there's an electric heater in there and it heats up the air. Okay, so that's sensible heat as well. So that would be an example of convection. So we looked at all different sorts of sensible heat sources there. We'll do one last one here. I think there's another one. So this is the reason I did this one is because it shows, see how the sunlight's coming in and hitting the door? See, it's 77 in the space, but the door is 89 degrees, right? That's because of the rate. This is a really good way to show radiant heat. So it's 77 degrees in the space. The sunlight's coming through the door, hitting that dark. It's coming through the window, hitting that dark door. It's really cool, by the way. That door is like 140 years old. It's amazing. We're in a very old renovated building here. And then this is the same example outside at 72. And then I point the laser gun at the deck, and I think it was 110 the day I did this. So just another example of radiant heat. Okay. There we go, 111. All right, so I think we've talked enough about sensible heat. The important thing is it doesn't matter how much moisture is in the air, okay? That's what sensible heat's all about. So latent heat's a different story. Latent heat is the amount of energy needed to cause a phase change in liquid. Well, in something, gas, liquid to gas or gas to liquid, okay? So think about it as the moisture content of the air. So when we're ever adding moisture to the air in a space, in a building, you're adding latent heat. So what devices do we have that add moisture to space? Well, just a sink will do that. That's supposed to be a water feature. That looks more like a mountain with a stream, but if you have a water feature, those put a lot of humidity into the space, by the way. People have, we generate humidity, latent heat, and then simple coffee cups, stuff like that on a pot. And I got a few examples here I'll show you. So this is the coffee warmer, and I like my coffee hot. This is like 190 degrees. Well, the warmer is, my coffee's not, but I like it blaring hot. So anyway, so that's sensible heat example. So if we want to look at what the latent component is, the best way I could think to show this is I put my moisture meter above it. The dew point was 58 before I opened the lid. Okay, so you can see how the dew point's going up. Yeah, swamp coolers. So you see, that's adding latent heat to the space. So that was the way I was showing latent heat. It was 58 degree dew point, now it's 87. So you can see that's adding latent heat to the space. Don't worry, there's no one in this shower, but that would add latent heat to the space as well. And then another coffee example, you can see it's 57.5 dew point. And I go up to the old Mr. Coffee machine, and you could see it's, the dew point's going up because it's adding latent heat. It's adding latent and sensible heat to the space. So I think that's a good way to show that. Little plug-in for the Mr. Coffee. Any Keurig fans out there? I can't stand them. I don't know why. They're so convenient, but they just don't. I love the old percolators, but anyway, we could probably up our coffee game too. So a big contribution to the latent heat of a HVAC system is any type of makeup air. This particular unit is 100% outdoor air unit, and you can see it's just pouring condensate off of there. That would be the latent heat of condensation, which is when the gas comes to a liquid. There's a latent heat of vaporization where a liquid becomes a gas. So those are the two types of latent heat. So, and there's just another cool shot to illustrate condensation coming off the coil. So it's amazing how much condensation a couple makeup air units will use during the summer. We'll produce during the summer. Okay, so we'll go through a few photos here. So just to look at this photo, take a look at this for a second. Think about what are the latent heat components and what are the sensible heat components while I have a sip of this steaming hot coffee. Okay, so I see a couple things here. There's a radiator in the back. Obviously, that if that was on, that would be sensible heat. There's radiant heat coming through the windows, and the heat off of the radiator would produce convection and conduction and radiant heat. The heat coming through the windows, radiant, conduction, convection if there's infiltration, which I'm sure there is. And then this being here, this cat is producing sensible and latent heat as well. So I thought that's a nice picture. It kind of illustrates a couple different things. This is how I feel my office is right now with all these lights and computers and everything. And again, I want to say thank you all for watching these videos. We're having a ton of fun doing them, and we're really appreciate the opportunity to give back. And we've been using these new online tools for a while now, and we really enjoy it. So, okay. So in this space, there's tons going on. A lot of dense BTUs happening here. You got all these people producing sensible latent heat. You got cameras, TVs, stage lighting. You've got some open water bottles. I don't see a whole lot of those, but a couple of those there. But you can see there's tons going on in that space, right? Okay. So sensible and latent heat examples there. Okay. Sensible and latent heat are expressed in BTUs. And a BTU is a British thermal unit. And we're still hanging in there with the BTUs. I think a lot of countries have moved on from the BTUs, but the technical definition of a BTU is the energy it takes to raise 1 gallon of water 1 degree Fahrenheit. Excuse me. So that's what that boiling pot is. All right. So in HVAC systems, we need to remove the sensible and the latent heat in the proper ratio so that we get the conditions of the design intent. So if you want it to be 72 degrees and 50%, you have to remove the proper ratio of sensible and latent heat. So that's why it's important to understand the difference between the two. Okay. And this is just to show what we typically do in an HVAC system. So when we're talking about moving from right to left, we're talking about sensible heat because we're getting cooler. When we're talking about moving down vertically, we're talking about removing moisture, which is reducing the latent component of the air. And we're typically moving in this fashion in normal everyday air conditioning systems. Okay. All right. So now we're going to do an example of calculating an SHR. And then on the next part, we're going to calculate the CFM using the sensible heat ratio and the psychrometric chart. So let's say you had this space. We'll just use this as a working example. And you got your favorite load program. And I was curious if folks would mind chatting what they use for their load program today. I won't get into all that company stuff, but anyway, I was just curious what people are using today as load programs. Okay, so let's say you got your load program out and you're doing your load profile of this space, and you calculate the sensible heat load is 80,000 BTUs. Thank you for the comments. Per hour. We express these in BTUs per hour when we're doing loads. And the latent heat is 20,000 BTUs per hour. Okay. What's your total heat of that space or that building? is 100,000 BTUs per hour because you're just adding the two. And that's your total heat. So the sensible heat ratio is the sensible heat divided by the total heat. And again, you'll get that from your load program, right? So sensible heat ratio in this case is 80,000 BTUs per hour divided by 100,000 BTUs per hour, which conveniently works out to 0.8 as your SHR, which makes it nice and clean. Okay, so what do we do with this SHR? So let's go to the psychrometric chart, and we're going to draw the SHR on the psych chart. Okay, so this particular psychrometric chart, the SHR is located right here. Sensible heat ratio. And if we want 0.8, we're going to go up to this designator right here. Okay, it's a little hard to see on the screen because there's a lot going on in psychrometric charts, as you know. Okay, so what we do is we find something called the index point, which on this chart is located right here. It's a unique point on the chart, and it's used to determine the slope of your SHR. So what you do is you locate the 2 points, the index point and the SHR, which is 0.8 in this case, and you draw a line like so, and that represents a 0.8 SHR on your psychrometric chart, okay? The one thing to note here is wherever you move that line on the chart, it represents a 0.8 SHR because it's a ratio. Okay, so as long as you keep the slope the same, no matter where you move it on the chart, it'll represent a 0.8 SHR. Okay? So here's why that sensible heat ratio is important. Remember, our room design intent was 72 degrees and 50% relative humidity. And we'll just show that by this dot here. Okay? So if we provide air to that space in a condition anywhere on this line, it'll result in our design intent of 72, 50%. Now, 0.3 will have a different CFM value than 0.1. You wouldn't want to do something like this because your face velocity would be huge. It'd be a lot of sound issues. It'd be like a tornado in there. That's the reason we do it down here. We'll get into all that later, but the point is to understand how SHR works, and if you know the SHR and you provide the right conditions, you will end up at your design intent, which is what this is all about, to remove the humidity and the heat so that we're comfortable in the space. Okay. Speaking of removing humidity and heat, what happens if we remove a lot of sensible heat, but not a lot of humidity? Well, we have a space that ends up cooler and damper, which is not a lot of fun if you've been in that situation. What happens if you remove a lot of humidity, but don't remove a lot of sensible heat? Well, you have a space which is too warm and too dry. So the purpose of this slide is just to show you it's important to get the ratios right. Okay. So we talked about air mixing. We talked about sensible heat ratio. Now we're going to talk about calculating air quantity, or CFM, cubic feet per minute. So I like to think of air as a sponge. It absorbs sensible and latent heat. If you introduce the right quantity of air at the right conditions, it will result in the space conditions that you're looking for. Okay, so we want that sponge to be cool and dry in a way that absorbs the heat and humidity in the proper ratio to give us our design intent. All right, so here's step one in calculating CFM. I think there's 5 steps. I can't remember, but we're going to go through the steps here. We'll find out. So step one, plot the makeup air temperature, the mixed air temperature, the outside air temperature, and the room temp. We do that right here. Won't go through all this, but we're going to go ahead. This is our previously calculated mixed air temperature. We're going to go ahead and label these. Point A is the OA, B is the return, and C is the mixed air temperature. let's take these over to the chart, and I won't spend the time going through all that. You can play this back and map them all out and plot them yourself. It'd actually be a good exercise if you're new. So A is your return air, B is your outside air, and C is your mixed air temperature. Okay. So we've plotted, and that's just defining each of the points. Okay, so that was step one. So step two, we calculate the sensible heat ratio, which we already did, which again is the sensible heat divided by the total heat. Okay, 80,000 divided by 100,000, which is 0.8. Now we're going to draw the SHR line. Okay, so now to remember, we're going to find our 0.8 SHR point on the right here. And I will note too, some charts are different. Not all of them do it this way. You could Google psychrometric charts and see all these examples, but the principle is the same. Okay, now we got to find our index point, which is right here, which is a little hard to see because it's underneath that line. There we go. And we're going to go ahead and draw our sensible heat ratio, which is a point from 0.8 through the index point. Okay, that's our sensible heat ratio. Now, what we want to do is move that sensible heat ratio to represent the space conditions that we're trying to achieve. Okay, so what we did is we just moved it down. We kept the slope the same, and we moved it down. Okay, and we connected it to the design intent, which is right here. Okay, which is what we're trying to achieve in our space. All right, so step four is to calculate the supply air conditions. Okay, there's a lot of different ways to do this. There's different schools of thoughts on it. What I like to do is show what happens is, let's talk about the process a little bit. So your mixed air temperature goes through a cooling coil. Okay, what happens when it goes through a cooling coil is it starts to cool sensibly first, and that as it approaches the 100% saturation line, water starts to condense out of the air, and you start going down in this fashion here. So you can just draw a straight line here, which is fine because we're just trying to find this point here that meets where the saturation meets the sensible heat ratio line. Okay. Okay. So if we were to plot this point, we see that it's about 49 degrees. All right. So just to recap, return air, outside air, mixed air, going through a cooling coil, intersecting with the SHR. Now, when you provide this air to the space at these conditions, at the CFM we're going to calculate, it'll absorb heat and humidity along the SHR and end up as your design intent. Now, there's other nuances here. There's supply fan heat gain, and there's return air duct pickup. You know, we're just keeping it simple on this. We're not going to show that at this point. So, okay. The other thing to point here, 49 degrees. The reason I did this example at 49 degrees is don't arbitrarily pick 55 degrees. You know, I don't know that a lot of engineers still do that, but when I first started, that was very common, but you can get into some trouble with that, okay? All right, now we're going to calculate the CFM. I believe this is the fifth and final step to calculating CFM. This is another one of those equations. If you're new, you're going to use this a lot, often. It's called the sensible heat equation. QS, sensible heat, in BTUs per hour, equals 1.1. We're going to talk about what that is in a minute, times CFM, cubic feet per minute, times delta T, the temperature difference you're talking about. Now, this delta T could be across a cooling coil. It could be the outside air or the supply air and the return air. It could be any delta T you want to calculate CFM, okay? Or calculate BTUs per hour, sorry. All right, let's talk about this mysterious 1.1. I call it a convenience factor. Last time I called it that, a bunch of people didn't like it on LinkedIn, so I might get some comments here, I don't know. The important thing to note that this is only 1.1 at standard air conditions, which is, I believe, 70 degrees and sea level. Okay, so if you're up in the mountains, in Breckenridge, Colorado at 10,000 feet, this will not be correct. So you have to look that up. So what it is, it's the density of air times the specific heat of air times 60 minutes per hour, which helps the conversions, ultimately to come out to BTUs per hour. Okay, and you can do all that. You can do cubic feet per minute, delta T, and all that, and you'll see that it comes out as BTUs per hour at the end. Okay, so density of air at standard conditions is 0.5 pounds per cubic. The specific heat of air, 0.241 BTUs over pounds degrees Fahrenheit, and then 60 minutes per hour equals 1.10. Now, if you've been around a while like me, I grew up in the industry using 1.085, and then a bunch of folks moved to 1.08, and now it's 1.1. I've changed this presentation 3 times to reflect that. I finally have gone on the bandwagon and am using 1.1. So, okay. So now we're going to take this equation and rearrange it and solve for CFM, because we're looking for CFM, remember? So CFM, sensible heat, divided by 1.1 times room dry bulb minus supply dry bulb, okay? So that's the delta T we're working with. So we fill this in. We know it's 80,000 for sensible. 72 degrees is our design intent. And then 49 degrees is the supplier, okay? So if you calculate this out, it's 3,200 CFM. All right, so now we go back to our constant volume system here, chill water system, and we plug that in here. So now we have everything we need to send our trusted HVAC supplier, the information. Hey, select this unit for me. And then you go through a few iterations and you got your unit. Okay, makes sense? I hope that makes sense. All right, so we're chugging right along here. Thank you again so much for watching. We just got one more section. We're going to talk about tons of refrigeration. And then I'm just going to show 2 slides on the full load, part load as a teaser to part 3, because this is really what we're trying to get at here. So tons of refrigeration. Okay. So a ton of refrigeration is 12,000 BTUs per hour, sometimes expressed as BTUH. Sure, you're all familiar with that, but you may not know where that comes from. This is actually kind of an interesting fact. So back in the ice making days, they determined it takes a 288,000 BTUs to melt, 1 ton of ice. Okay? If you take that and divide it by 24 hours in a day, it takes 12,000 BTUs per hour to melt a ton of ice. Okay, and that's how we get, that's why we call it tons, apparently. Interesting, huh? So there you go. Now you learned something new and you can share that with your family today. Kind of useless information, but I like the history. I don't know why. So, okay, tons of refrigeration, total heat gain equation. Here's another one, to go along with your list of equations if you're taking notes. So the mixed air temperature calculation, the sensible heat gain equation, and the total heat gain equation. And most psychrometric charts you get will have a lot of these formulas on there. But if you don't have one, write it down or go print one, online. You can have that. So, okay, so let's double click on this equation. I hear a lot of people say that, but it's kind of annoying to me. But I'm going to say it anyway. So here's another mysterious convenience factor, 4.5. To note again, be careful with this. So it's BTUs per hour equals 4.5 times CFM times delta H. Total, the T is for total. Okay, I didn't mention that. And then we're going to convert it to tons. Okay, so total heat equation, density, 60 minutes per hour. Okay, kind of what we did before. So the important thing to note here is that if you're at a higher elevation, be super careful with this. You don't want to mess up a load if you're, 5,000 feet or 10,000 feet. You can really severely cause some major issues. All right, so delta H, what is H? H is enthalpy, okay? What is enthalpy? Enthalpy is the total heat energy in 1 pound of dry air, okay? So I have my, Heather loves them when I do this, by the way. So what does a pound of air look like? So a pound of air is 13.5 cubic feet. This is about 9 cubic feet. So you could just, this was a little bit bigger, it would be a pound of air. So that's what a pound of air looks like, a pound of dry air. Thank you, Tom Peterson with CDI for showing me that example there. Heather said I'm like Bill Nye, the science guy. Okay, I'll take that. I've been called worse. Okay, so that's 1 pound of dry air. Total heat energy in 1 pound of dry air. So enthalpy includes all the heat energy, the total, the sensible, the latent. You know, this is a good little video showing, you know, the total heat energy of the air coming out in condensation or whatever. Okay, so let's move on here. All right, so we're going to calculate the total energy of this airstream going across the coil through our fictional unit we were looking at earlier. Okay, so what do? What do we have to determine that we haven't talked about yet? We have to determine the enthalpy. So we need the delta H. So we're going to use the delta H of the air entering the coil to the air leaving the coil. And that makes sense because we're trying to find out the tons of refrigeration of the coil, right? So we want the enthalpy here and the enthalpy here. So just as a refresher, enthalpy on this chart is located over here, okay? And what you do is you take the point you're trying to find the enthalpy of and you line it up on both of these enthalpy designators on both ends. Okay, so see how I did that? Again, it's a little hard to see, but you would basically line it up here and here and draw your line so that both enthalpies equal and then it falls through that point. Okay, that's the best way I could think of saying that. So in this case, it is 29.8 BTUs per pound of dry air entering the coil. And will the enthalpy be less or greater leaving the coil? Let you think about that for a sec. So the enthalpy, the total heat energy of the air would be less leaving the coil, which is shown here. If I get my clicker to work. Okay, 19.5. So 29.8 enthalpy, 19.5 enthalpy. So what is the tonnage of refrigeration? Now we have the data we can use to plug that in to see the tons of refrigeration. So to see the total heat in that airstream. Okay, we're going to convert that to tons because this comes out in BTUs. I keep saying tons because I'm looking at the T and my brain's going crazy. But so 4.5 times CFM, which is 3,200, which we calculated before, times enthalpy 1 minus enthalpy 2, which in this case is, make sure I said that right. Yep. Okay. Which happens to be 148,320 BTUs per hour. Now, how do we convert that to tons? If you remember from the last slide, there's 12,000 BTUs per hour in a ton. So we divide it and we get about 12.36 tons. 12-ish tons, okay? All right, so we're chugging along. We're almost done here. We talked about air mixing, sensible heat ratio. And Heather, if you don't mind putting up the QR code, we get a lot of people asking where to rewatch this or if they want to share it. And that's the QR code where we're going to actually it's streaming there live now so people can watch it right after this event if you want to zap that or share this video. Calculating air quantity and tons of refrigeration. And now we're going to just spend about 2 or 3 minutes talking about full load and part load and why this is extremely important to understand sensible heat ratio. And while we're doing this, before you go, if you don't mind liking this video, we'd appreciate it. So, okay, let's talk about part load for a second. So again, I've said this a few times. So I've been in the business for over 25 years. One of the biggest mistakes we see is folks designing systems that are not prepared for part load conditions. Okay. Most cases, it may not be that big of a deal. If it's general office space or something like that, we pretty much know what's going to happen there at part load. If you're in a big auditorium, a big church, a grow room, incredible things happen when you turn the lights off in grow rooms. Okay, I don't know if that's technically a part load condition, but it is a different SHR. So understanding what happens at part load is extremely important when you're designing HVAC systems. And I'm going to show you why psychrometrically. Okay, we're going to get real nerdy on this for a minute. But if you look at our full load SHR, our full load conditions, 80,000 over 100,000. Let's say you had a part load day. It's October. It's cool and rainy outside, or where it's overcast. Let's say that. So that brings your sensible down to 47,000 and your total down to 67,000. So now your SHR is 0.7. It went from 0.8 to 0.7, okay? This was the previous system we had looked at a 0.8 SHR, all right? So remember, this example has a chill water air handling unit. It's approximately 12 tons. It's 3,200 CFM. It's constant volume. So at part load conditions, when you don't need 49-degree air, what can you change on this system? You probably could change the leaving air temperature because it's a chill water system, and you could throttle the valve and provide a higher leaving air temperature, okay? What air temperature would you provide at this SHR to make it work? Well, you could use your sensible heat equation and solve for supply dry bulb so that you meet the sensible load requirements in the space at 47,000 BTUs, okay? So your new supply air temperature, because it's a part load day, is going to be 58.4, which is significantly warmer than the 49. So why is that a problem? I'll show you why. Funny you should ask. So if you draw 58.4 on the psych chart, we'll call that D prime. So this is where we were. This is where we are now, leaving the coil. And we take our 0.7 SHR, which is the new SHR. So see how the slope's different? We're drawing that through the index point to get the slope, and we move that up to D prime. We get a new space condition of A prime. Now, who can recognize the problem there? The problem here is we were at 50% RH. Now we're at 70% RH. Okay? So is that a problem? I don't know. Maybe. Probably in most cases it would be uncomfortable at the least. In some cases it could be devastating. If it's an archival storage or if it's a surgery suite, pharmaceutical manufacturing, etc. So the point here is just to illustrate, when you have a change in SHR, you have a change in the slope. You have to change something, sometimes the supply air, temperature. But anyway, this right here is the exact reason why so many systems fail to control humidity at all load conditions, because if it were me and I was designing this, I would have, probably the ability to change the CFM. Or if it was a DX system, I would have modulating compressors, hot gas reheat, which is extremely important to dehumidification control, which is one of my favorite ways to do it. You could have recovered energy reheat. We get into all that at part 3. So, okay. All right, so you all are probably sick of hearing about this stuff. And let's see, we talked about air mixing, SHR, calculating air quantity, tons, full load, part load. And if you have any questions, throw them in the chat. I'm going to throw a few questions here. You can play along. I think we've met all the requirements of the PDH, but you can stick around. I have 5 questions here. So the sensible heat ratio is determined by dividing the sensible heat by latent heat, true or false? Ted says, or a school library with a DX at night down south. Yeah, could be a huge problem for sure. So the sensible heat ratio is determined by dividing sensible Latent heat, true or false? That is false. The correct answer is total heat, not latent heat. So it's divided by latent heat. I see a lot of good answers coming in here. Thanks for all the great answers. There's a delay of about 30 seconds. So when it comes out of my mouth to when you hear it is 30 seconds different, but the chat works in a different fashion. So I usually see them come through after I give the answer. So I'll slow down a little bit. Okay, so latent heat is the energy needed to cause a phase change and is associated with the water content of the air, unlike sensible heat. True or false? So many right answers for the first one. While y'all are answering that there, I'm going to just again thank you all so much for coming. You can scan that QR code. The PDH credits are, PDH certificate is available through my email. Just shoot me an email. And this answer is true. I see a lot of correct answers there. Thank you very much. I love the engagement, by the way. Thank you so much for doing that. It makes this so much more enjoyable. And I know it's all about my enjoyment. I know that's why you all come here, right? So write out the sensible heat equation. Not really a question, but maybe I should reword it. Can you write out the sensible heat equation? Then the answer would be yes, not the sensible heat equation. So give that a few seconds here. And I think for part 3, we're going to probably do that in, what month is it? September? Maybe middle October, something like that. And also be on the lookout for our PDH marathon, which we do in December, which is a lot of fun. We had 4 hours of PDHs online we streamed that live on our website. That was a lot of fun. If you have any topics you want to see, let us know and we'll try our best to incorporate them. Most of the time, the topics are kind of like determined by who's available to present at what time. But that's a great way to get some PDH credits if you don't have them by the end of the year. So how many BTUs per hour is 1 ton of refrigeration? How many BTUs per hour is 1 ton of refrigeration? There's an interesting story on the history of ice making, by the way. There was a doctor in the Panhandle. I want to say Gorey. I might be misremembering that. But he invented a contraption to make ice for the patients who were suffering in Florida. And I believe it was from malaria. But he made ice, and the ice was hung from the ceiling, and by convection, the air was cooled, and it gave relief to the patients. He tried to patent it, but the folks who were making ice or were harvesting ice weren't too excited about having a machine that would take their job. So he got kind of shut down. Interesting history. That would be a cool PDH class, the history of air conditioning. I don't know. It'd be cool to me. Every time I post stuff like that, nobody likes it. So maybe just the only one. All right. I think this is the last question here. In the tons of refrigeration equation, QT equals 4.5 times CFM times delta H. The 4.5 is a constant and does not need to be adjusted for air density. True or false? Thank you, Gabrielle. So, yep, this one is false. Please be super careful of that. Yeah, Heather, you could put the chat overlay. Let's try that. That's pretty cool. I didn't think about that. This Q&A is actually a lot of fun. Maybe next time we just, if you need to run, please do. You've met your requirement for the PDH, but I think that was my last question. Dang it. Next time I'll just have a bunch and we can just hang out. Maybe we'll give away some Insight Partner mugs or something like that. But yeah, a lot of people got the answer right. Okay. You can leave the overlay up. That's pretty cool. Thank you, Heather. We'll do that next time. Good call on that. So are we done yet? No. We have Psychrometrics Part 3. Yeah, Heather had a good point. Why don't you put in the chat some topics you'd like to see on the next PDH or in the PDH marathon? If we can find the answers to that, we'll we'll do that topic. That would be great. So the next presentation is Psychrometrics Part 3, Controlling Temperature and Humidity. And we really go through the part load example we touched on today. We really go through that in depth, and we talk about different types of constant volume systems to control, humidity at part load. Phase and bypass is one of them, or turn air bypass. And then we talk about reheat, which is one of the most popular ways to control humidity at part load, especially with all the advances in, DX with modulating reheat, modulating compressors and stuff like that. So, okay. All right. I want to personally thank you all for joining us. Please like and share this video if you haven't yet. Please email me for your PDH credits. And thank you so much for joining us. We hope to have the registration for the next event up soon. And again, you can message me and get your PDH credits. And thank you so much for joining us. Heather, you can hit the outro. Thank you.